Okay, cool. So you guys are lucky because I realized that I should cover slightly different topics. For like which I think make more sense. So what that means for you guys is that you guys are gonna get the longer end of the stick. So you guys are gonna see nicer topics. Well, not really nice. So what I mean by that is that for the previous tutorial classes I covered hashing and quicksort. But now that I think about it, covering both of them doesn't seem to bring about that much value. So what I'm going to do for you guys is I'm going to show you guys quicksort, but I'm also going to show you guys this thing called majority voting, which both use different techniques. So you should get some value. You should get like some added value out of it. Hopefully, like the other tutorial classes can watch the video. Okay, so let me jump straight into it because I remember that like at least like yesterday when I tried to do the two topics, even though they weren't very heavy, it still took 50, like, almost exactly 15 minutes. So that's like, yeah, we really don't have much time. So let me do my best to explain this and let's see if I can cover both things. Okay. Covering both things would be, let's see, something like a lecture and a half material of last semester. So let's see if I can squeeze that in 15 minutes. I guess this is a challenge to myself as well. Okay, so let's talk about quicksort. Now, I understand that you guys have already seen the analysis of average case quicksort once during lecture. I'm going to show you a different way to do it. And the reason why I think there's value in the way that I'm showing you how to do this is because the way that I'm showing you uses indicator random variables, which is the thing that I told you about last week, right? And I said, oh, these things are really good. There's a wide range of use for this thing in analysis. So what I mean by that is that the stuff that I'm going to show you, you can use those ideas like really similarly to do other things. Like if you've heard of treeps, for example, treeps are, if you've not heard, is a randomized data structure, which is a marriage of heaps, your binary heaps, and binary search trees. So somehow someone asked, was probably high off weed, and he asked the question, what happens if you try to make a binary search tree, but there was also a heap? You get a treep. So a treep is really much just like a randomized, like imagine randomizing your input and then inserting into a binary search tree. What kind of height should you get? That sort of thing. These questions or hashing questions, for example, a lot of these can be answered using the same techniques I'm about to show you. Okay, so yeah, okay. Again, I'm in a rush. I shouldn't get sidetracked so much. Okay, so let's begin. So usually for quicksort, like we want to ask the question, what's the expected running time, right? Expected running time. So the first step to this is always saying that, okay, there's going to be some random variable t, and I want to find the e of t, right? In other words, at the end of the day, right, this is my end goal. I want to find what this is. Okay, but let's just ask what t is first as a random variable. Very similar to what we did last week, right? And like if you recall, as a quick summary, last week we dealt with geometric random variables. If you don't remember, that's fine. Go watch the video. I can't do a full recap here, right? And so last week's moral of the story was how to use geometric random variables. This week we're going to talk about indicator random variables first, and then I'll talk about some other special stuff later on. Okay, so if I have a random variable t here, which talks about the expected, or sorry, not the expected, a random variable t here, which models the running time of quicksort, right? One question to ask, if I want to use indicator random variables, is going to be, what should I be indicating? Okay, so at the end of the day, right, like very similar to last week, I still want to express this as a summation of some variables, right? The only question is going to become, what should those variables look like? Or what should those variables be? Okay, and the hint here I'm giving you is that they should be indicator random variables, meaning I'm going to sum over variables this time around, which are not geometric, which instead take on values either 1 or 0. All right, and they, of course, they take on 1 with some probability p, which we will discuss later on, and 0 with some probability 1 minus p. All right, now, so at this point, right, if you're at this step, right, your thinking process should be asking yourself, okay, so someone's told me that I should be using indicator random variables, and I want to make it a sum, and these indicator random variables should somehow talk about my running time, right? So we should ask ourselves in quicksort. What should we look at that is correlated, or is that that which directly talks about the running time, right? And the first thing that comes to mind is the comparisons. right? The running time should be, proportional to the number of comparisons that you make, right? Because every time you make a comparison, that's where all the magic happens, right? The quicksort algorithm looks at two elements, makes a comparison, and then optionally makes a swap, right? Whether it makes a swap or it doesn't, the point is that a comparison was made, so that adds to the running time. Okay, the next question you might want to ask is, okay, is there anything else that adds to the running time? Yeah, possibly you might need to swap the pivot once you're done with the partition step. You might need to, push some variables into the recursive call stack, for example. But for the most part, you know that you're going to do at most n swaps, and you know that you're going to push and pop from the stack at most, like, on average n times or something. So O n times or something. So no, I mean, even in the worst case, it's like n, right? So this is fine. Okay, so we don't really have to care about those things. The only thing that really matters here is the number of swaps, right? And you might be wondering, yeah, but you know what if the plus n makes a difference, right? The answer is no, it doesn't, because you had to run at least one partition, even in the very best case, you have to run the partition algorithm at least once, right? So you know the running time of quicksort is at least n, right? So you can just pretend that, pushing your variables onto the recursive call stack, for example, or swapping out the pivots, which happen at most n times across the whole execution of quicksort, should just be counted under that n, right? Then the only thing that we care about now should just be the number of comparisons being made, right? And we know that on a bad day we have to make a lot of comparisons, right? If it was very lopsided, for example, on a good day we don't have to, right? So the question becomes, what about in between? Like maybe we're not always lucky, maybe we're not always unlucky, so what should that look like? Okay, so what I'm trying to say is that you should convince yourself that the running time should be proportional to the number of comparisons being made between all possible pairs. So here's how I'm going to write the summation. I know it looks pretty scary, but let me write it down first, and then I'll explain what it does. J is equals to I plus 1 and xij. Okay, now this guy here is going to be an indicator random variable that says 1 if AI is compared to AJ. Now let me explain what this is in a minute. This is not what you think it is. Compared to AJ. 0 otherwise. Okay, so this is again an indicator random variable, and what it says here is that okay, maybe I should not use A. A is a bad idea, because this might cause some confusion. So let me put SI and SJ. Let me explain what this is in a bit. Okay, no, let me explain it right now. So your input comes in an array, right? So we'll say an input array, and you would expect your input to be like A1, A2, AN, right? Okay, what I'm saying is that we should also think about what the array looks like when it's sorted first. All right, we don't have the sorted array, all right, but we know it exists, so it's fine to consider it. As long as whatever we do, doesn't, like, whatever our algorithm doesn't need to understand what's going on, doesn't need to understand what the sorted array looks like, right? So this is for the sake of analysis. Remember, like, for us, right, what we're gonna do here is that we're gonna actually try to map some of the input back to the sorted array and do some analysis, right? But our algorithm doesn't have to understand this. Our algorithm just has to run as as it should. Okay, so I'm gonna say S1, S2, Sn, and we know that there is some mapping from the input to the sorted array, right? So in other words, like, there is some way for you to shuffle the elements, so that the input array is going to become the sorted array, something like that. Right? I don't know what it looks like. The point is that it should look something like this, right? So okay, so just not more than 2 minutes ago, what I said about this was, hey, so the expected running time of quicksort, we should think of the running time of quicksort, you should think about it as the number of comparisons being made, right? Between any two pairs, right? So in other words, right, what I'm saying is that at this point, I can go around between every pair and say, okay, like, you two of your elements, were you compared? Two of your elements, were you compared? Two of your elements, were you compared, right? So I could go here and say, hey, the two of you, were you compared? Right? Or maybe I could ask, hey, the two of you, were you compared? And I need to do this for every pair. Okay, so the limits of this summation give me that, right? My I will range from 1 to n minus 1. Okay, my j will range from I plus 1 to n. Okay, so what this means is that when I fix an I, right, and my I here goes from 1 to n minus 1, my j here only fixes values that are larger than I to n. So this really goes through, iterates through all pairs. So in other words, right, at some point, you should think about this as like, I mean, again, this is S not, sorry, should I say S or I? Sorry, this is a sorted array, right? So you know, like at first we want to say, okay, going through all the inputs, we'll ask every possible pairing, like, hey, will you compare? Hey, will you compare? Hey, will you compare? That sort of thing. But asking it on the input array is the same thing as asking it on the sorted array, right? Because if they were compared in the input array, they're also the corresponding elements are going to be compared in the sorted array. And since I'm asking this of all pairs, right, it can't hurt for me to ask it on the sorted array instead of the input array. Right. When I say ask it on the sorted array, I don't mean we're running quicksort on the sorted array. I'm saying we're running quicksort on the input array, okay, but we'll ask the corresponding question on the sorted array. All right. So this is kind of important. And I hope this makes sense to you guys. Because if not, you have to stop me and let me know. All right. So I'm just gonna say it one more time in case anyone didn't catch that. Okay. Like I said, that we're gonna say the runtime of quicksort is proportional to the number of comparisons being made. Right? So what we should be doing is counting the number of comparisons being made across any two pairs, right? So the way to do that is to actually go across, technically the way to do that is to go across the input and pick any two pair and ask, hey, were the two of you compared? You know, like we'll ask that question on them, right? Like let's say AI and A7 or something, okay? But since, you know, we know that the sorted array is just a shuffle of the input array, okay? Instead, what I'm gonna say is, okay, let's say for example, A1 maps to S2, and let's just say that A7 maps to, like, let's say S5, okay? Then asking A1 and A7 whether they were compared is the same as asking whether S2 and S5 were compared, right? And since we know that everything here is just a shuffle of everything here, if I ask a question to a pair here, eventually I'll be asking the same question to some pair on the sorted array instead. Okay, now I know at this point it's confusing. You might be wondering, why do I have to ask this question on the sorted array? Okay, the answer will become really apparent. By compared you mean whether they will compare against each other, right? Yes, that's right, whether they will compare against each other. All right, so I know it might be confusing now. Why do we have to do this weird thing? Why can't we just ask it on the input array? All right, the answer is going to be that it will be very easy for me to tell you what the probability is once we think about it from the perspective of the sorted array. All right, even though quicksort runs on the input array. Okay, so just bear with me on this for now. Right? Okay, so compared against each other doesn't mean they will eventually swap, right? Yep, it doesn't mean, that's right, it doesn't mean they're eventually swap. That's an astute observation, but it doesn't matter because the point is the comparison was made, right? In the worst case, you can only swap as much as you compare, right? So the running time should still be bounded by the number of comparisons, not by the number of swaps, right? Because if all of the comparisons lead to a swap, that's just 2 times the running time, right? So we don't really care about that, right? What we care about is just the number of comparisons being made. But you're right. Okay, so that's a nice observation to make. Okay, so let's get back to this, right? Before I move any further into the analysis, right? Let's do the very nice thing right now and say and ask what is the E of t. All right, I know that the E of t should just be the E of this guy by linearity of expectations. So I know that this should just be the sum, you know, across like the same limits, right? I'm not gonna write them anymore to save space. This is just going to be the probability that xij is equals to 1. Right? Because I mean, by expectation, you know that it will be 1 times the probability that xij is equals to 1 plus 0 times the probability that xij is equals to 0, right? But 0 means that the term disappears. Okay, so this is the same as asking, what is the probability, right? Summed across all the i's and j's, right? What is the probability that si is compared to sj eventually, like at some point in time, is compared to sj at some point in time. Okay, so at this, so the whole point is that as long as I can get this out, we're done with the analysis, right? I can just plug in the exclamation and hopefully we can deal with it somehow. Okay, so that's our task now. Our task now has reduced from trying to deal with this very weird, this very difficult random variable to a very simple question: when is Si compared to Sj? Okay, so again, I need to draw the two arrays. Let me draw it here. So what was the input? I think input array was red, right? I hope the input array was red. Okay, let's not use red anymore. I don't know. It looks like such a scary color. Let's use purple. Okay, so we have the input array. So the input array, like let's say, looks like this: A1, A2, A3, so on and so forth until AN. Okay, and the sorted array looks like this: S1, S2, until Sn. So remember, right, that when I say sorted array, right, it's the same elements as the input, but you have to shuffle it you have to shuffle it from the input to get the sorted array, right? So in other words, like maybe the elements have to go like this or something, right? Think about it like that. Like remember that this has to happen. Okay. Now let's ask ourselves, when is Si compared to Sj? Okay. So there's going to be an Si somewhere and an Sj somewhere, right? Which corresponds to I don't know, let's say some AI and some AJ, right? So it has to correspond to some, let's make that green, some AI and some AJ somewhere, right? For all we know, like AJ could be before AI, but in the sorted version, it's the other way around. It doesn't really matter. Okay, now what's randomized quicksort going to do? At this point in time, randomized quicksort is going to randomly pick a pivot, right? So in other words, it could, let me use a different color for this. It could randomly pick a pivot, which is something here or something here. Oh, I actually need a lot of space for this. Oh, 1 second. Actually, no, I don't. I actually don't worry about it. Okay, it could randomly pick a pivot in the array, right? So in other words, any of these guys could be picked in the array. This guy, this guy, this guy. Sorry, this guy, or like, you know, so on and so forth. Any of these guys could be picked, right? And randomly picking any of these guys as a pivot, okay, first of all, it's the same as randomly picking any of these guys as a pivot in the corresponding sorted array, right? Now I know that sounds a bit confusing, but what I'm trying to say is that when you randomly pick a pivot in the pivot, okay, wait, let's talk about this. Let me clear out some space. When you randomly pick a pivot in the input array, okay, what happens after that? If let's say I picked A2 as a pivot, right? We know that everything in the array is going to be compared against it, right? And let's just say that A2 is like, let's say sitting somewhere here in the sorted array, right? Then what happens to the rest of the input? We know that everything here is going to be to the left of, everything on the left of it is going to be smaller than it, right? Which means that the left half of the sorted array is going to be the same, right? And we know that everything on the right is going to be larger than it, which means that anything on the right half of the sorted array is going to be some shuffle of the right half, right? But the point I'm trying to get at is that if let's say I randomly picked A2 and A2 corresponded to some element S, I don't know, let's call it SP, which was the same element on the sorted array instead, right? What we can think of is that when I say I pick A2 as the pivot, okay, and I'm going to put A2 here. Sorry, when I pick A2 as the pivot, it's the same as saying I picked SP as my pivot, right? And then what's going to happen is that I'm going to say, okay, I know every element here in this array is compared to it. It's the same as saying every element in the sorted array is compared to it, right? Even though the algorithm works on the input, right? The point is that I can still say the same. The comparisons don't change, right? I know that if I pick A2 as the so again, let me say that one more time. If A2 was picked as the pivot, right? I know that everything in the input array is compared to it, right? It's the same. If A2 is the same element as SP, right? It's the same as saying if SP is picked as the pivot, everything on the array is compared to it. All right. This I know this probably sounds a bit obvious, and you might be asking, why do we have to do this? The reason will become clear in a minute or two. But I hope this makes sense, right? Like whatever I've said so far should make sense, right? Okay. Okay, so now I kind of actually want to use this. Okay, so again, remember what we care about is AI and AJ. Okay, so the question becomes, when is AI and AJ picked as a pivot? Sorry, when are they compared to each other, right? Now the thing that you have to realize is that it's only going to be compared to each other if at some point in time, right, they were sitting on the same array, right? They were sitting on the same array, and one of them was picked as a pivot. Right, so if AJ was picked as a pivot, right, you know that AI in sitting in the same array is going to be compared to it, right? And we actually care about SI and SJ, right? So I should actually be asking the corresponding question on the sorted array. I should be asking, hey, when is SI and when is SJ going to be compared to each other? Right, there can be elements in between. That's fine. So if SI is picked as a pivot, you know that SI is going to be compared with everything in the array, right? So SI will be compared to SJ. In other words, then Xij will have to say 1, right? So in other words, it will have to say 1 if Si is picked as pivot. So this part is fine. Okay, now what else could you pick as a pivot so that they're compared? You could also pick SJ, right? So if SJ was picked as a pivot, you know that it has to be compared against everything in the array, right? When I say SJ is picked as a pivot, I don't mean the algorithm looks at the sorted array and picks SJ, right? What I mean is that the algorithm looks at the input array and picks AJ. But I know this is the same as picking SJ, right? And then what will happen is that, you know, like AJ is compared to everything in the input, which is the same as saying SJ is compared to everything in the sorted array, right? So then SJ is compared to SI, right? So it should also say one if SJ is picked as pivot. Okay. So now the other question is when should I say 0? Okay. So this might be a weird question to ask, but if you think about it, right? What if at some point in time my quicksort picks some element on the side here? Okay. So like for example, right? Let's just say that there was some element, let's say S5, okay, and S5 maps to some element. Let's write that in red. So there's some element S5, and let's say this maps to I don't know, A20 or something. Okay, and let's say that our algorithm picked A20 as a pivot. All right, so we know that corresponds to picking S5 as a pivot. Okay, what should the input look like? What should the input array look like after this? We know that A20 in its sorted position is both to the left of SI and both to the like it's left of both SI and SJ, right? So after partitioning, what should happen is, wait, I need space, let me clear this out. So we know that after partitioning, had I picked A20, which is the same question as saying, had I picked S5, right? Had I picked that to partition, I know that sure, S5 will be compared to I and J. That's not the question that I want answered, right? The point is that SI and SJ are still going to be sitting on the right side of the partition, right? So then a quicksort will be called here and a quicksort will be called here, right? So can I, given on the event that I know that S5 was picked as a pivot, can I say something conclusive about whether SI or SJ was eventually compared or not? The answer is no, right? I don't know. Because for all we know, right, further down in this recursive call, eventually SI is going to be picked as a pivot or SJ is going to be picked as a pivot, right? So in other words, what I'm saying is that if I have some element that is to the left of both SI and SJ that was picked as a pivot in the input array, right? I can't say whether they're being compared or not, right? I really don't know. So the moment the algorithm picks something on the outside of the pivot, if you ask me, hey, given that you know that this element that was far off on the side was picked as a pivot, right? Do you know whether SI was compared to SJ? The answer is I don't know, right? Because further down the recursion, like SI could be picked as a pivot, SJ could be picked as a pivot. We really don't know. So the answer is that it's inconclusive. Okay. So likewise, same for the right side of the array. Okay. If let's say that there were some elements here, okay, that was picked as a pivot. Okay, which again, you know, like what this means is that you pick, let's say for example, A1, and A1 was, let's say, Sn minus 1, right? So you pick this as a pivot and you try to partition using it. Is the same as saying, what happens if I have an element here and I'm trying to use this as a partition, right? You know that because you pick this as a pivot, you can't say whether SI is compared to SJ or not yet, at least, right? Maybe further down the line in recursion, the same reasoning applies. SI could be picked as a pivot eventually. Okay, so the moral of the story here right now, as of right now, is that if something is really far off on the side, it doesn't matter. Okay, we really don't know anything. Okay, so the next question is, okay, what about, we know that if I pick SI or SJ, we know that it will be compared, right? We know that if we pick something on the far side, it will not be compared. What about if we pick something in the center, right? So what if, like, say for example, I pick something like SI plus 2 as my pivot, right? So SI plus 2 could have been, let's say this oh, sorry, 1 second, this element here. Let's say SI was this one, SI plus 2, this element here, and my algorithm picked this as a pivot, right? I know that after partitioning, right, SI is going to be sitting on, so let's say SI plus 2 is here. After partitioning the input array, right, we'll have that SI is on the left side and SJ is on the right side, right? So what does this tell you? This tells you that SI can even if SI is picked as a pivot eventually, right, or if SJ was picked as a pivot eventually, they can never be compared against each other anymore because they are in different calls of quicksort. All right. So to summarize what we've seen so far, if I look at the input array, okay, I know that anything that was picked if I'm asking the question whether Si was compared to Sj, if something if something was picked as a pivot that was outside of their range, right? I can't say anything, okay? But if within their range, right, they were picked, then I know that they were compared to each other, okay? And if within their range, something in the middle was picked instead, they were not compared to each other. All right. So this is just a really long essay for me to say what I want to say. And what I want to say is that if I want to ask the question of whether xi is compared to xj, okay, you very simply need to ask, if I look at the sorted array, okay, and I look at this subarray of the, if I look at this boundary of the subarray, okay, the question becomes whether within this range, si was picked or sj was picked. If two such elements were picked, then I know that they were compared to each other. If any other element in the middle was picked, then I know they were not. I do not have to care about elements on the side. They do not matter to me. All right. So, okay, this is a really messy drawing. Let me clear this up. Okay. Oh God, it's like construction going on, like renovation going on in my area right now. It's really loud. Do not matter as in neither 0 nor 1. Yeah, that's right. So it's not 0 or 1. Because if I'm asking the question whether whether Si is compared to Sj, right? And I know that something else on the outside was picked, right? It doesn't say anything, right? So my random variable should not conclusively give me 0 or 1, right? It should only give me 0. It should only give me 0 if something in the middle was picked as a pivot. It should only give me 1 if either Si or Sj itself was picked as a pivot, right? If something else was picked as a pivot, the random variable shouldn't give you a value yet, right? Eventually, something's going to be picked as a pivot, and when something's picked as a pivot, you know that the random variable will give you an answer, right? So in other words, right, like you know that if I okay, so I hope this is clear enough, because I'm running out of time and I really want to cover something else as well for you guys. Okay, so what I'm saying is that, okay, so let's focus on this array. So all I'm trying to say, like from that, was that, hey, if I want to talk about Si and Sj, we should just focus on this subarray. Okay. Now, when we talk about randomized quicksort, right, we're randomly selecting pivots, right, which means that in this range, right, there must be some pivot that is randomly chosen, right? Okay, so if I'm going to randomly pick a pivot within this range, okay, and there are elements from Si to Sj, how many elements are there in this set? Okay, so that's going to be j minus I plus 1 elements. Okay, the off by 1 is because, like, what, it's from I to j. It's not from I to j plus 1 or something. Sorry, j minus 1. Anyway, so I'm going to pick any element here as a pivot, like within this set, with probability 1 over j minus I plus 1. That's because I have this many elements, so I pick all of them with equal probability. So that has to be 1 over j minus I plus 1. Okay. Now the probability that I is compared to j is when either Si was when Si is compared to Sj is when either I pick Si as a pivot or whether I pick Sj as a pivot, right? So that happens with 2 times the probability that I pick some element, because I have 2 elements that I can pick now that are good, that are bad, right? When either of these are the pivot, right? So this is the probability that I pick either element as a pivot. And if I pick either as an element as a pivot, I know that they will be compared to each other, right? Which is what I care about. Okay, so after that really long analysis, if you still don't get it, like, you can watch the video. If not, ask me the question on Telegram, right? I can't answer any more questions right now, because if I do, I will not have time to cover the next topic, which I really want to cover. I know that this is summed across from I to n minus 1, j is equals to I plus 1 to n, right? This is just me copying over the limits. And I want to replace this probability with this actual value here, right? So this is 2 over j minus I plus 1. Okay, now I know this summation might look scary, okay, but the way that you should think about it is that, okay, so the way that I would tackle this, okay, is I would think about what the terms look like. Okay, I know that if I were to fix a value I and just focus on this summation alone, right, the value that I start off at would be 2 over 2. Okay, and then the next value would be 2 over 3. And the next value would be 2 over 4, right? And I mean, okay, so without the summation, right? And then after that, at what value do I stop this summation? The value that I stop this summation would be 2 over, let's see, I plus 1 minus I plus 1. So that would be, it would be when, it would be n, right? So it'd be n minus I plus 1, like that. And this is summed across all I, right? I from 1 to n. Okay. Now, this might look a bit weird. You might not know how to handle this, right? Let me factor the 2 out first so it looks a bit cleaner. So this is summation from I equals to 1 to n. This is 1 over 2, 1 over 3, 1 over 4, until 1 over n minus I plus 1. Okay. Now, this again still kind of looks really scary, but let me make this an inequality, right? So bear in mind over here, I'm saying that I'm gonna make this, I'm gonna show that this sum at the top is less than some other sum at the bottom, right? The reason why I do this is because it'll be more obvious what this is. 1 over 3, until 1 over n minus I plus 1, right? Then let me add more terms into it, right? So I'm gonna keep going all the way until 1 over n. So what is this? This thing right here is actually just the harmonic series, right? So this can be written as from I equals to 1 to n ln n, right? Which is the same as 2. This n here right now is like we're summing ln n times, so that's just n ln n. Very roughly n ln n. All right, so what have we proven? We've proven that the average case, the average number of comparisons that have to be made by quicksort, right, is n ln n. Okay, so in other words, since we know that this, again, by our argument, should like correlate to the runtime, you shouldn't be doing much more work than you do comparisons anyway. So the average case running time of quicksort should be n ln n. Okay, so what's the moral of the story here before I move on to the next thing that I want to show you guys? The moral of the story here is that, well, last week the moral of the story was that, hey, I have some random variable. I don't know how to deal with it. I would express it as a summation of geometric, right? And then I would say the expectation of that random variable was the summation of the expectations of the geometrics. And then I know from the geometrics that it should just be 1 over p. All I have to do is figure out what the value of p is. And hey, it's a good day for me, right? I can complete the analysis. Likewise over here, right? I have some very, very tricky situation that I want to analyze. Something like running time of quicksort, which is not trivial, right? Like it's a bit hard to predict what should quicksort do, right? So then what we would say is, okay, so let's try to talk about what random variables do we care about, right? So you could do the same thing for hashing, for example. You could ask how many collisions happen, right? So you could, for example, let's say, what's the worst case running time? What's the average case running time of let's say hashing n items into a table with chaining, right? Then you could say, oh, you know what I can do? What I can do is that I know that the length of a chain should be like the number of collisions that happen or something like that. You could just make a random variable that looks like this, and you could just sum across all of them. Something along those lines, right? The point is that you could always try to analyze your algorithm through your data structures by looking at these events in isolation, right? You just look at any two I and j and say, oh, something should happen here. And if something bad happens here, I should take that into account. And as long as you add all those values up, right, it should account for all the costs that you need for either your algorithm or your data structure. And you would realize that it's even though it's kind of like still possibly potentially a bit challenging to deal with these kind of random variables, it's a whole lot easier than to deal with something as complicated as this. All right, so that's the moral of the story, like thus far. Okay, if you have a random variable that you need to analyze, sometimes you should just express it as some. Moral is that math is spooky. Yeah, well, math is spooky. Like that's true, right? But it's worth the effort to learn and figure out. Like you're never gonna use this have this excuse to pick these up at any other pick these things up at any other point in your life, you know. So let's move on. Let's move all this out. Okay, so let me do something slightly more natural. When I say natural, I mean like slightly cooler, or like, you know, like the first time that I saw this, I thought, wow, the guy who did this analysis was like high off his boots or something. But I don't have much time. So again, if you have any questions about the quicksort, I know that the analysis for this is a bit confusing, or is a bit scary, because I have like I'll tell you guys right now, right, that quicksort analysis that I showed you is typically covered in a module called CS3230. So in other words, right, I've just used this as an excuse to show you something from a 5K module. So I wouldn't expect you guys to, like, you know, if you guys are confused at this point, that's fine. You know, please ask me questions on Telegram, and I'll try to answer them as best as I can. But this is the best way I feel like I can explain the analysis to you. And the reason why I did it, I took the risk to do this because I think the technique is really good. And you can use this for other things. Eventually you realize you can use it for other things. All right. But I don't have time to cover it now because, okay, let me stop lamenting. Let me save time. Let me move on to the next thing. Okay, so let's do one more thing, right? The one thing that the other tutorials didn't get to see, which I think is also very useful. Okay, let's talk about majority calculation. So let's say I have an array, and this array has only either zeros or ones. So it could be like 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, blah, 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 1, 1, 1, that's it. So this is the array that I care about right now. Okay, it only has two values, 0 or 1. And I want to find what the majority value is. Okay, so the majority value, and I'm promised it's going to be a majority value, but it's not what you think it is. I don't want to say the majority value is the one that's more than half. I want something called a supermajority. So in other words, right, I'm going to call an element a supermajority if it happens at least 2/3 of the time in the array. So if the array is of length n, right, let's say 0 is a supermajority. If 0 happens at least 2/3 of the time, 1 will be the supermajority if it happens at least 2/3 of the time. Okay, but if neither of these elements happen 2/3 of the time, you can imagine like an array with half-half, then there is no supermajority. Okay, so that's for sure, right? You might ask me the question, yeah, but can't we have like no supermajority? The answer is yes, but let's not care about that. Let's pretend the array always has a supermajority. I just don't know which it is. It could be 0, it could be 1, okay, but it can't be neither. It has to be either one of them. Okay, so let's think about what's the best deterministic algorithm you could come up for this. Oh wait, let me ask this question. Did Divesh cover supermajority in lecture? Please tell me he didn't. Nope. Okay, good. Then you guys are gonna see something nice tonight. I mean today, this morning. What is it tonight? Okay, anyway. I'm still asleep, I guess. Okay, so let's talk about this. What's the best deterministic algorithm you could come up for this? Like deterministic, fixed, right? So no randomization involved. Okay. Like you could say, maybe I will fix some very specific way to probe the input, right? But at the end of the day, you still have to read off the array on the zeros and ones, okay? And in the very worst case, right, what's going to happen is that you need to read through at least 2/3 of the array to figure out what the supermajority. Sorry, I guess you might need to read through 1/3 of the array to figure out what the supermajority is. Should I say that? Something like that, right? Because the point is that unless you read this fraction of the input, right, you can't be sure. It could go either way, right? Like for example, if you see like a third of the zeros, oh no, I guess you have to read through 2/3, right? You could see, yeah, it should be 2/3. You're right. It should be 2/3, right? Because in the worst case, right, no matter how you probe it, there's going to be some input where you see a third of the zeros first and a third of the ones, right? A third of the ones before you either see the next 0 or 1. Yeah, that's right. It should be 1/3 plus 1/3. That's right. You're right about that, right? So again, let me repeat. In the worst case, right, no matter what deterministic algorithm you come up with, there is going to be some input where you're going to end up seeing a third zeros first and then a third ones, right? And then after that, you need to read one more bit to decide which one is a supermajority. Okay, so deterministic algorithms are bad. They need at least n time omega n time here. Okay. But with randomization, we can somehow actually escape this linear time constraint. Okay, which I think is pretty cool. Okay, so this is a new technique. Okay, nothing geometric, nothing indicator. Okay, let's see if I can do it in like 10 minutes because I have to let you guys go at 9:50. And then I guess if you have to go, you can catch up on the video hopefully later on. I hope this is okay. I hope this arrangement is okay with you guys because I think I will have to end up eating over time, a bit. Okay, so what we're gonna do is we're gonna think about this recursively. All right, so I think like Martin Hens would like to say something along the lines of, hey, like we can do recursion or like bring this up to divide and conquer or something. I don't know if he does that. I actually never took 1S, but I would like to think that he feels that way. Okay, so we're gonna take our input, okay, and chop it up into 3 parts, a third each. Okay, so I know this doesn't look like a third, but we'll pretend this is a third of the array each. This middle third looks really big. Okay, so what we're gonna do is we're gonna recursively call the supermajority algorithm. Okay, we're gonna call the supermajority algorithm here. We're gonna call the supermajority algorithm here. We're gonna call the supermajority algorithm here. Okay. Now the thing that you need to notice, right, is that since there is a supermajority somewhere, okay, it's going to happen that if 0 was a supermajority, right, at least 2 out of 3 of these algorithms should return 0 as the supermajority. right? So if you do a back of the envelope calculation, let's just pretend 0 is the supermajority. The same argument holds if it's 1, right? You know that that 2/3 of n, at least 2/3 of n is zeros, right? So there is no way you're going to be able to distribute. Wait, is there a way for you to distribute these into? Could you? Let me think. No, right? Because like that, let me see. So in the best case, okay, so think about how you would try to distribute these things, right? And you'll realize that no matter how you do it, at least two of these guys are gonna have a lot of zeros, right? Like in the worst case, you could try to spread out all the zeros, right? But remember, each array has to be of size 1/3 n, right? So then like by this, I don't know, some ratio argument, it should all the majority should be 0, right? So I don't know how to prove it. I don't want to take my time proving it. I know I can prove it. I just don't want to waste the time doing it. Just take my word for it. That at least 2 out of 3 of these guys should return 0 as a supermajority as well. Okay. So likewise, if it's 1, right? If 1 is a supermajority, there should be one of these two that should return 1. Wish you could do that for exams. Well, hey, if this is an exam, I would spend less time trying to explain it and more time trying to solve it, right? Okay. So fine. So what I'm saying is that we can think about this recursively, right? All I need to do is call 3 supermajority votes, get their answer, and then return the majority of that. Okay, so that doesn't seem to be an improvement right now because my recursive relationship says Tn is equals to 3Tn over 3 plus O1, right? And if you still remember your master theorem or like whatever it is, this should still be On. Okay. But it's no longer guaranteed that each subarray contains a supermajority. Is it not guaranteed? I'm pretty sure it is, right? You could it could be 2 don't have, yeah. So it's not that for all, right? It could be like, for example, let's say 0 was a supermajority. Let's say 0 was a supermajority. The best guarantee I could give you is that this guy returns, for example, both these guys return 0, this guy returns 1. That could be fine, but I don't really care, right? The point is that I'll see 2 zeros and I'll say, okay, so this is a supermajority. I return 0. Right? I'll ignore the 1 on the side. That's what I'm trying to say. All right. So I hope you're convinced with that. But right now, right, there doesn't seem to be an improvement in the running time. Okay. The reason why is that I'm still making 3 recursive calls, right? And this is on inputs of size n over 3. So if you solve for this recurrence, you realize this is still O(n) time. Okay. Okay, fine, but I've not done any randomization, right? So the way that I'm going to do it is that I'm going to randomly pick let's say this is A, this is B, and this is C. Okay, so the algorithm now is going to be, I'm going to randomly pick 2 from the set ABC. And I'm going to run the supermajority algorithm on each. Okay, so in other words, right, with some probability, I'm going to run, let's see, how many combinations are there? 3 choose 2. 3 choose 2 should be 3. So I'm either going to pick AB, or I'm going to pick AC, or I'm going to pick BC. Okay, and I'm going to start with these two and ignore the third guy. So over here, I'm going to ignore C. Over here, I'm going to ignore B. Over here, I'm going to ignore A. Okay, I'm going to run supermajority on these two first. So SM on the first, SM on the second, or SM on the first, SM on the second, or SM on the first, SM on the second. Okay, now the nice thing about this is that no matter how you arrange the inputs, right, I know that whatever the supermajority is, right, okay, on a good day, I pick both correct parts such that they hold the supermajority. So let's pretend 0 is a supermajority. Our algorithm doesn't know this, but this makes my argument easier. You can swap it out for 1, it doesn't matter. Okay, so let's pretend 0 is a supermajority. So we know that in the worst case, right, only 2 of these guys have 0. So maybe it's A and B. I don't know, right? And C is the one with the that is not the supermajority, right? That isn't like has 1 as a supermajority, but that is not our supermajority, right? Okay, it could be this case. So on a good day, right, if this happened, like on a good day, I randomly pick A and B, right? And again, the adversary has no control over this. I have no control over this, right? It could try to arrange the inputs however it wants. We just know that I'm going to randomly pick it, right? Like for example, it could have arranged it with the 1 in the middle instead. That's fine. The point is that I'm going to randomly pick it, right? So let's just pretend this is the way that it's picked for the sake of an illustration. The way that it's arranged for the sake of illustration. And on a good day, I was lucky, I picked A and B, right? I run both supermajorities, right? So this is only 2 recursive calls now, okay? And I find the supermajority. I see both zeros, right? At this point, do I have to care about C? The answer is no, because I already know that the supermajority value is 0. So, you know, what do I have to care about? I don't have to care about anything. Okay, so okay, fine. So I know this. Now, so what, with what probability does this happen, right? So I know that with probability, if let's say it was arranged in this way, right? The only good arrangement that could happen is this one out of the 3 arrangements, right? In a bad arrangement could be that I randomly picked, let's say for example, A and C, okay? And it just so happens that when I picked A and C, one guy returned 0, one guy returned 1, right? Then I still don't know what the supermajority is. I have to recurse. I have no choice now. I have to recurse on B, right? So I know that if my inputs were arranged in a sort of quote unquote worst case manner, which is that only 2 of them have a supermajority and have the correct supermajority, and one of them have a different supermajority, right? With probability 1/3, it's a good day for me. I make 2 recursive calls. Okay. On a bad day, right? On a bad day, I have to make 3 recursive calls. So 2/3 of the time, I have to make 3 recursive calls instead of 2. Okay. Now, each of these supermajority algorithms is randomized as well. So they also repeat this randomized process by themselves. Okay. So in other words, what I'm saying is that if I want to ask what is the running time of my algorithm, let me use a nicer color. If I want to ask what's the running time of my algorithm, and let's pretend this is a tree, right? So we can think of this as a tree. So we can think of this as a recursive tree with 3 branches, right? So on and so forth until a leaf, right? And a leaf should only have either 1 element or 3 elements or whatever. The point is that we can think of this as a tree with some height h, right? We know h here should be log base 3 of n. The log will now matter because it's going to be in the exponent. Okay, so the expected running time of this algorithm at height h, okay, is just going to be with probability 1/3, right? 2 calls of the expected running time. Okay, let me write that better. Sorry, that didn't look very nice. With probability 1/3 is going to be 2 calls of the expected running time of the algorithm on h minus 1, okay, plus 2/3, right? The 3 calls that happen, right, with the expected running time of h minus 1. When I say h minus 1, I mean like this is like recursing down 1 level, right? So we know that the input size is decreased by a factor of 3. Okay, so fine. I know that this means that it'll be 2/3 plus 3 2/3, right? So it will be 2/3 plus 2 3 3 here, e of h minus 1, right? Which is to say that this is the same as 4, sorry, not 4. I have 8/3 of e of h minus 1. Okay, and I know that e of, let's say, e of what? Let's say e of 0, e of 1 or 0, I don't think it really matters. E of 0 is, let's just say 1, because you still need to read the array once, right? So if it's a single element, you still need to read it and report it as a supermajority. Okay, and now we know that this is very nice, right? So in other words, what I'm saying is that e of h is just 8/3 of e of h minus 1, right? So let me clear this out. Okay, so what I'm saying, I'm almost done. What I'm saying is that e of h, right, is 8/3 of e of h minus 1, right? Which, if you manually expand it, right, is going to be 8/3 squared of e of h minus 2, right? And so if you keep going down the recursion tree, you just keep roping in a factor of 8/3, right? Okay, but how many times do you have to go down? You have to go down at most to h times, right? So it should be 8/3 to h. I might be off by 1. I don't think it matters too much. That should be fine. Times 8 e0, and I know that e0 is going to be 1, right? So e of h is the expected number of comparisons you need to checks you need to make. Even though you're at height h, is just going to be 8/3 to the power of h, right? And I know h here is log base 3n, so that's going to be, what is this? This is 8/3 to the power of log base 3n. Okay, now let me just whip out my phone real fast because I want to compute this value. Okay, let me do some quick math. This I know is n to the power of log base 3, 8 over 3. And this is going to be, where's my calculator? Let's see if anyone beats me to it. You know, your calculators don't have like log base 3, so I need to write this as something like, what was it? If I want to do change of bases, I need to do log base 10, 8 over 3 divided by log base 10, 3, right? I think. Correct me if I'm wrong. 8 divided by 3. This whole thing divided by log 3. I should be correct. Okay, so this, assuming I plug the correct value into my calculator, this should be n to the power of 0.89. So this is much, this technically speaking is much smaller than n, because n is like n to the power of 1, right? Okay, so what's the moral of the story here? Well, again, if you randomize things work out nicely. I mean, okay, it's more than that. What I'm trying to say here is that, okay, so what have I shown you? I've shown you how to use geometric random variables last week. I've shown you how to use indicator random variables earlier today. And the last thing here is that if you're really high off your variables recursively, and sometimes it all just works out very nicely. Oh, by the way, right, just so we're clear, since we're here and since you guys are here, I might as well say, okay, I know that we when we say O log n, right, and you might be asking, hey, what base? Remember, I always tell you that the base doesn't matter here, right? Because if it's log n here, you know that if you want to change a base, to change something from base A to base B, right? Like log base A to log base B, all you have to do is just divide by like log base BA or something like that. And if A and B are constants, this log here is this log thing here is a constant, right? The reason why the base here matters, okay, is because it's in the exponent. Okay, so had I changed this to log base 2 instead, there'll be a constant that pops out here on the side. And that constant that pops out here on the side is going to pop out here on the side. Right? And that constant might push this guy up like to more than 1 or something. The point is that there's going to be some constant here. And if you have a constant exponent, that actually slows your algorithm down, right? So when I tell you constant, the base doesn't matter for a log, it's only when the log is not being used as an exponent or something else, right? If it's being used by itself, you know, not being raised to the power of anything, like it's not the power of anything, that's fine. But if it's the power of something, start carrying. That's when it's important. Okay? Let's see, moral of the story, a lot of work for small optimization. Yeah, I mean, this is why our degree has, is this a Monte Carlo algorithm? I'm not very sure. I don't do Monte Carlo. Oh my God, it's drilling. Why? A lot of work for small optimization. Yeah, I actually have something to say about that. It's like, a huge reason why you're learning CS, or you know, like a huge motivation behind CS is not software. It's actually to make things run efficiently. That's the name of the game. So the whole point of your degree, the value of your degree, is so that you know how to do these optimizations. You know, it should be Las Vegas since you always use the correct answer. Oh yeah, I guess that's true. I don't know. I don't really bother classifying these algorithms. Wait, where was I? I got sidetracked. Right. So the whole one. Okay, I wouldn't say the whole point of it, but like a majority of why you're spending your school fees and a majority of why you're spending 4 years in university is not so that you can just write code. Because I'll be honest now, any monkey can write code. Like I can write code too, and I'm pretty sure I'm a monkey at it, right? Part of the reason why, okay, like you could say part of the reason why is training in software engineering, right? Which is to, what was it? It was to communicate. It's to, there's like, I don't know, my friend said there's 3 main reasons for software engineering. Like you have to know how to communicate, you need to know how to document. I think document is part of communicating. You need to know how to, I don't know, work together or something. I can't remember anymore. Abstraction or something. It's not really my concern. Right, but a huge other reason why you're in CS, or a huge reason why CS is something that's like non-trivial, and something why you have why we need to give, why we need you to stay here for 4 years, right, and spend so much time on it, is because there is a lot of work that goes on into optimization, and part of CS is about optimization. It's about working faster than normal people would know how to do. Like if you were to randomly pick a person on the street and give them this problem, they would still give you the same algorithm. They would say, okay, you know what, I'll just count the values, right? What else can you do, right? Like how else would they? Because they don't have the tools to do things like this, right? And this is part of the value of a degree. It's so that if for example, right, someone someday, you know, requires you to design such a solution, right? You'd be able to do it. You'd be able to say, hey, in the worst case, my algorithm runs in n time, right? But that's fine, because sometimes it's going to run faster than that. Right. So that's one of the reasons why you're here, or that's one of the reasons why CS is a thing. It's because some of us like to twiddle around with these numbers and get really fast solutions that no one else can dream of. So yeah, that's all I have to say about that. I sound preachy. I sound like some old man trying to like oh, you kids these days don't understand what CS. but yeah, I'm just saying, like, if it's never occurred to you, there's a reason why there's so much work that goes into this. It's part of the value of your degree. It's part of what we expect computer scientists to offer to the world. The ability to optimize things. And it's not easy. If it was easy, we wouldn't have it in a degree. You know, we would have it in, I don't know, high school or something. Like, we would expect anyone to be able to do it, right? But that's not true. Right? So I mean, I don't know if you like feel proud about that, but for the quick one, can I ask why we sweep the cases well outside of IJ under the rug? Right. Okay. So before I answer your question, so at this point I have to say officially class is over, right? So if you have to go, you have to go. It's fine. Okay. If you're worried about missing out on anything else, just I'll let you guys know, and you guys can catch up on the recording, like, if that's okay, right? But whatever I'm gonna say now is just gonna be answering questions. Okay. So, like, if you have to go, that's fine. Thanks for sticking by. See you guys next week. Okay. So let me get around to answering your question. So for the quick one, can I ask why we sweep the cases where it's outside IJ under the rug? Okay. So again, you want to think about let me write down the input again. So AI to A2, so on and so forth until AN, right? I'm going to leave this blank for now, but remember there are elements in between, okay? And I want to think about the sorted array S1 to S2 to Sn, right? And I hope this is already clear to you that these are just, the sorted array is just a shuffle of the input array, right? Okay, so let me think, what was I going to say? Oh God, that drilling upstairs is like really ruining my thinking process. Okay, so remember what randomized quicksort does? What randomized quicksort does is that it's going to pick some element AP here, and it's going to use it as a pivot. Okay, at some point in time, right? Now this corresponds to it picking, let's say, SP, right? Which may not be sitting on the same spot, right? This could be somewhere like far down the middle of the array. This could be on the side of the array. This is why I drew them on the side, just to illustrate that point. If I pick this element as a pivot, right, it's the same as me saying, hey, I picked this element as a pivot, right? And when I say that this element is now going to be compared with everything in the array, right, this is the same as saying I'm being compared against everything else in the array here. Okay? So that's the first thing you need to get. The second thing that you need to get is that if I pick AP as my pivot, right, think about what happens to the input. So after picking this as the pivot, right, what's going to happen is that AP is going to sit, it's actually going to sit exactly where SP is sitting, right? And then everything here is going to be a shuffle of everything here, right? And everything here is going to be a shuffle of, sorry, yeah, everything is, I drew the wrong thing. Let me do that again. So everything here is going to be a shuffle of everything here, and everything here is going to be a shuffle of everything here, right? So I know these don't look very related, but you need to bear this in mind because this is very important, okay? So I'm gonna trust that you understand this. Okay, so let's move on to the question about why do we not care about when AI is compared to AJ? Okay, so let's say that and when I say AI and AJ, what I don't mean is like, okay, sorry, I didn't mean AI and AJ. What I meant was SI and SJ, right? So SI is here, SJ is here. Okay, so let's say that corresponds to, I don't know, some AP. I can't use AP. Damn it, AR and AS. Right. So let's say that this corresponds to this and this corresponds to this, or the other way around. Doesn't really matter. Okay. When I ask the question, hey, was SI compared to SJ? Okay. Let me get rid of this. I actually need that later on. When I ask, hey, is SI compared to SJ? Right, it's the same as asking, hey, was either of them picked as a pivot, right? Which is technically the same question as asking, hey, was AS picked as a pivot, or whether, I'm confusing myself. Is AR picked as a pivot, or is AS picked as a pivot, right? So that part is fine, right? So then I told you something along the lines of, okay, so instead of asking whether AR is compared to AS, we will always just look at SI and SJ and ask whether they were picked as a pivot. That it shouldn't hurt ourselves to think about it from that sense instead, right? Now, the thing is this, at this point in time, right, at this point in the execution, why am I only drawing straight lines? That's weird. Okay. At this point in time, right, of the input, okay, oh, sorry, here. Okay, like if I were to pick some random pivot here, right? Let's say something on the left of SI and SJ. Okay, now let's see. So what's going to happen is that if I pick something here, it might correspond to something in the middle. That's fine, right? So maybe something here. Okay, I pick this guy as a pivot. It's the same as saying I pick this guy as a pivot on the input array. Then I'm going to partition based on this. When I partition based on this, right, SI and SJ are going to be on like after. Okay, after this partition, what happens? It's going to be the case that whatever this element is here is now sitting here. Okay, and this part of the input is a shuffle of this part of the input, right? And this part of the input is a shuffle of this part of the input. Okay, and we still have to continue, right? Quicksort still needs to pick pivots, right? So what kind of pivots can Quicksort pick now? Quicksort can still pick pivots here, or Quicksort can still pick pivots here. Okay, but if I were to pick a pivot here, for example, okay, actually no, that's fine. Let's not talk about that. I mean, the point is that Quicksort still has to continue, right? So I can still ask questions. I can still say, hey, was S1 compared to S2? Right? I know that S1 and S2 are like on the same side of the array here, right? So I can still ask that question. I can still ask, provided that a pivot that was on the right side of them, right, was picked, right? I can still ask this pair, hey, were either of you picked as a pivot and compared to each other? That's fine, right? So what I'm trying to say is that if I pick something on the outside range, right, it doesn't affect the value xij. So what I'm trying to say is that given that something outside Sij was picked, right? So something, let's say St, where T is like either on this side was picked. St is here or is here. Given that St was picked as pivot, right? Does this affect the value of Xij? So I'm asking, what's the probability that Xij is equals to 1 given that St was pivot? I still don't know. I still don't know what this value is, right? It's still, I only care about this value when something in the middle was picked as a pivot, or something here was picked as a pivot. If something on the outside was picked as a pivot, Quicksort still eventually has to pick a pivot around this portion of the array, right? Quicksort could pick some pivots here, Quicksort could pick some pivots here, right? The issue is that there's still not a pivot picked here, right? And Quicksort still eventually has to pick a pivot there, and it could either pick something on the border or pick something on the side, right? But until then, I like this. Knowing that something on the outside was picked as a pivot does not change the probability. Does that make sense? I'm trying to figure out a different way to explain this at the same time, but I'm not really sure how I would explain it now. Because you've not said, oh, okay, like the usual time. So like how people usually do, which means that I'm guessing I've not sufficiently convinced you yet. Okay, let me try to figure out how. Let me try to find a different way to explain this. How would I explain it? I'm really not sure. Since we took E is picking exactly IJ. Since we took cases between IJ outside as, wouldn't your expectation formulation break down because of it? Since we took E is equals to picking exactly IJ. Since we took cases where it's between IJ outside as 0. What do you mean by that? I don't get your question. As in, my formulation was this, right? T expected of T is equals to sum across the ij's, right? And then I would say expected of xij, right? So are you saying that there could be some correlation between the xi's and the xj's? Like, as in, like, for different i's and j's? Like, if conditioned on the fact that I pick something as a pivot here, then something else should have returned 0 somewhere else, like something further out, right? Like, if I pick something here and this was 1, then the thing here should be 0 or something like that. Is that what you're trying to say? Uh-huh. I mean, we didn't simplify xij to, we simplified the expectation of xij to that value. Xij gives you 0 or 1. The expectation of Xij is 2 over j minus 1 plus 1. right? So in other words, what I'm saying is that if I were to apply E here, then this is the same as, we drop cases outside. No, it doesn't mean that it will evaluate to 0, right? Because, okay, so Xij here, right, is either 1 or 0, right? So Exij here, right, is 1 times the probability that Xij is equals to 1, plus 0 times the probability that Xij is equals to 0, right? And I'm saying that over here, right, this is the same as saying the probability that Si is compared to Sj. Oh, why is there construction going on? Si is compared to Sj, right? Which is the same as saying 2 over j minus I plus 1, right? So again, given that something outside the range was picked, right? So if this was Si and this was Sj, there's something in between, right? The point is that if something here was chosen, right, or if something here was chosen, okay, like it doesn't affect the value of Xij, right? Given that something here was chosen, I cannot say that Xij should now be 0 or Xij should be 1. I can only say, like, if, okay, so when can I say it's 0? I can say it's 0 here. If something here was picked, then I know Xij is equals to 0. If something here was picked, I know Xij is 1. Right? If something here is picked, I can't say anything. Means we drop cases where it's between Xij equals to 0. So yeah, I'm not really sure what you're trying to say when you say dropping, but picking outside will reduce the probability. Will picking outside reduce the probability? Sure, but the thing is that over here, like, okay, when I say given, it's just an intuition, right? The point is that if I look at Xij itself, there is no given. Right? So this ties into the fact that we're looking at the linearity expectations, right? So it's highly unintuitive, but it's like, if you think about it, okay. So if you're asking this question, right, let me give you a slightly, like, a more toy example that illustrates the same point. All right. I didn't want to cover this because it was actually very easy, but I think it does the trick quite well to explain this question of yours. Like, does it reduce the probability, and how it should look like? It's called the hat check problem. Okay, so the hat check problem is one where you have n people that go into a restaurant, okay, and they throw their hats in. I'm not gonna write it down, but basically there's gonna be n people, right? They came to a restaurant, and this was the days before we had social distancing, so they all threw their hats in the pile together, and the hats are indistinguishable. I mean, when I say indistinguishable, I mean they can't tell whether, like, it's their own hat. We know, but they don't. Okay, so there are n people and there are n hats. Okay, now the hats are shuffled. So this is going to be, you just think of this as this being shuffled. Okay, at the end of the day, once they're all done with dinner, they all leave at the same time and they all randomly pick up a hat. So at this point, you might be asking, right, hey, like, when you say randomly pick up a hat, does, like, the first person pick a hat first, then the second person pick up a hat? How does this work, right? The answer is it actually doesn't matter, right? Or you can, you can think of this as, I take the hats and I shuffle it, and then, then, like, whatever the shuffle is, right, that's going to be, whatever permutation it is how the people receive it. You could think of it like that as well. It's fine. Okay. So then now the question I want to ask is, what's the expected number of people who get their hats back? Expected number of people who get their hats back. Do you know the answer to this? So this might sound like a difficult question, right? You might want to you might want to use the definition of expectation and say, okay, let's say E of H, right? Then I will say, oh, the probability that H is equals to 1, like only one person gets his hat back times 1 plus the probability that H is equals to 2 times 2, so on and so forth, right? Like, no, that's way too complicated. So let me show you the nice way to do it. So the way that you're going to do this is you would say Xi is equals to 1. Yeah, it should be 1, right? So the reason why it should be 1 is that okay, so let me write this down. So it's Xi is equals to 1 if ith person gets his hat back. Person gets his hat back. His or her, I guess. Girls can wear hats too. hatchback. 0 otherwise. Okay, so what's the expected number of people who get their hats back? It's just a summation. I mean, so I can say the total number of people who get their hats back is the sum across all the people who get their hats back, right? Now, the E of x is really just summation of E of xi. Okay. Now, at this point, you might be saying, yeah, but the xi's can be correlated, right? Given that someone got his hat back, right? Someone else might like it might be more likely for someone else to get his hat back, right? Because if I have my hat back, right, then I don't have your hat, and if I don't have your hat, right, it's more likely that you should be getting a hat back. If and given that, for example, let's say I don't have your hat, right? I have someone else's hat, right? So that means that I know at least one of the xj's, which is not me, should also get 0, right? Because I have someone else's hat, so which means that someone else has my hat for sure, right? But the nice thing about linearity of expectation, right, is that even if the random variables are correlated, the sum still works out, and you can actually prove this. I mean, I can prove it for two for you right now. So let's say I have 2 random variables x, y, and they're correlated, right? So in other words, what I'm saying is that it is not the case that for every probability x equals to x and y equals to y, you know, like I don't need this assumption. I will never need this. So I will not need the assumption that they're equals. In other words, what I'm saying is that there's going to be some values where this is true, right? But that's fine, because if I look at the expectation of x plus y, this is sum across both the x and y's, right? X plus y times the probability that x is equals to x and the probability that y is equals to y, right? Then this is a sum, you can just split it into 2 parts, right? So this is summation with x, xy, summation with xy, x plus, this part is x, just x, and then this part comes down, this part is y, this part just comes down, okay? Now I'm summing across x and y here, right? So let me just rewrite this. This is sum x, probability that x is equals to x, y is equals to y times x, plus y times the probability that y, so that the x is equals to x and y is equals to y times y. Okay, but if I'm summing across all the xy's on this part, okay, think about how it works. So if I fix a value x and I sum across all the y's, right? Eventually, all I get is the marginal. Wait, do you know marginals? I don't know if you know marginals. You should just think of it as, okay, if I'm summing across all possible x and y's, right? If I fix an x, I'm summing across all the y's that occur with it. So that's the same as saying the probability of x, right? So if I fix some value x and I sum across all the possible values of y, it's the same as just saying, oh, the probability that x occurs, right? So the first part of the summation just boils down to summation of x times the probability of x, right? And this part here, right, is the same thing. So this becomes y times the probability that y is equals to y. This gives me E of x. This gives me E of y, right? So as counterintuitive as it seems, right, even in the hat check problem, you can see that there's clearly a correlation in the random variables, right? The same way, picking something outside as a pivot should affect your chances, but the linearity expectation says that you shouldn't care about it. The math works out. It just so beautifully works out when it's undetermined in our calculations. When I say undetermined, right, what I meant by undetermined is that, okay, I'm trying to think of a different scenario where some random variable has been quote unquote undetermined, and I've never seen it. Okay, the point is that you should properly define your random variable. That's what I'm trying to say, right? I think okay. So the reason why there's some uncertainty right now is probably because I actually failed at explaining this xij thing. So what I can try to do is spend a day sitting on it and figuring out a better explanation for you. and then when I figure one out, I'll send it to you on the Telegram group. Does that work? As in when it's outside, isn't it undetermined? Yeah, I guess I would say that. It's an event that we don't care about because it's none of our concern, right? we can drop all those cases in our calculation. Yeah, because it's unrelated, right? It's irrelevant to our concern of Xij. I mean, if I pick something outside the pivot, right, like outside that range, right, quicksort still has to pick something inside it eventually, right? Some comparison has to be made to separate Si and Sj, right? Like that has to occur. So when that happens, right, you know that what do you know? Yeah, you know that some pivot in between has to be chosen. So something outside the pivot, right, doesn't tell you anything at all. It's irrelevant. Yeah, that's how I put it. I mean, like that's the way I would write it in an exam if someone asked me that question. All right. Okay, cool. So this was way over the Q&A was way over time. Oh, but yeah, thanks for asking those questions, because it's really good when you guys tell me you're uncertain, because at least this way I know how to like fix it for you guys. And congrats, like you guys sat through like a level 5,000 topic. So yeah, okay. So if there are no more questions, or I mean, if there are any more questions, send them on Telegram, I guess. And then yeah, that's all. I'll upload this video to YouTube when I get the chance. But otherwise, I hope you guys have a great weekend ahead. See you guys next week. Gonna end the meeting now. Bye bye. No worries.